Hello everyone, welcome to the last lecture of the mini course Computational Mathematics. For the last few lectures we are working with univariate polynomials. Namely, we develop methods for finding roots of a single univariate polynomial. As I said last time, today we will concentrate on a problem of solving systems of multivariate polynomials. To this end, we will apply methods of so-called Grobner bases. Grobner bases form one of the pillars of so-called elimination theory. Elimination theory is not a new theory, it is a theory which started in the mid-19th century with development of so-called resultants. Resultants were developed mainly throughout the second half of the 19th century, and the theory of resultant culminated in the very famous, very important result of Macaulay from the first decade of 20th century. However, after that the theory became a bit stalled. It looked like the theory is completely exhausted and there are no new results developing in concerning elimination theory, to the extent that in 1940s Andrew Weil, one of the very famous algebraists, said that elimination theory should be eliminated from the textbooks. This statement made reaction from Sharam Abhyankar, who said that the eliminators of elimination theory should be eliminated. In fact, he wrote a poem, Polynomials and Power Series, which was published in Mathematical Intelligencer. Surprisingly, in the second half of 20th century, elimination theory was revived. It was due to the completely new results invented in the mid-1960s by Bruno Buchberger. Bruno Buchberger defended his PhD thesis in 1965, in which he presented methods of so-called Grobner bases, which we will learn today. Grobner was actually the supervisor of Bruno Buchberger, and Bruno Buchberger wanted to somehow present his gratitude to his supervisor and called this new device Grobner bases. And it turned out that in the last about 50 years, theory of Grobner bases and more generally elimination theory was one of the most dynamically developing theories in mathematics, with hundreds of results concerning both Grobner bases, resultants, and some other devices like, for example, border bases. So today you will learn some of the basic facts concerning Grobner bases, and you will see how we can apply Grobner bases for solving system of multivariate polynomial equations.
Before we dig into any details concerning Grobner bases, let me first explain a general idea how elimination theory works, no matter whether these are Grobner bases, resultants, border bases, or any other type of elimination. The whole idea is to take a system of multivariate polynomial equations and eliminate all the variables except possibly one. So just to give a concrete example, consider the following system of two bivariate polynomial equations. On this example, I will explain how elimination theory works. We can think of both these equations as equations describing plane algebraic curves. So the first line is an equation of the blue curve, which you can see here, And the second line is the equation of a red curve that you can see here. It follows that the solutions to the system of these two equations are precisely the points where these two curves intersect, because these are the points where both equations are satisfied simultaneously. So it follows that here, 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 and here, these are the solutions to the system. These 6 points where these two curves intersect are precisely the solutions. So the whole idea of elimination theory is to use some device, for example, the Grobner basis that we will develop today, to use this device to get rid of one of the variables. So, in fact, to eliminate one of the variables. So, this is where the name comes from. So, for example, we eliminate a variable y. So we arrive at a univariate polynomial equation that supports only x. In general, this equation will be of quite a high degree, and in fact, generally, the equation of the eliminant of this single polynomial that you get will be the product of the degrees of these two polynomials. So here it's 4 times 4 gives 16. So we have a single equation of just one variable of high degree. And the important thing is that the roots of these equations are just the abscisas of the solutions of the original system. So it looks like this. This was our original system. The solutions were the points where these two curves intersect. And this is a graph of a polynomial we obtained by eliminating one of the variables, in this case, variable y. And the roots of these polynomials, there are 6 real roots. These roots are just projections of the solutions of a system. So if we project, for example, this point, we project it on the y-axis, we will get exactly this root of the polynomial. So this guy is here, and so on concerning all the other roots. So by eliminating a variable, we arrive at a single polynomial of just one variable, such that the roots of this polynomial are the projections of the solution that we are looking for. So what we can do now? There are actually two possibilities. First of all, we need to find the roots of this univariate polynomial. In our case, the real roots are these 6 numbers that we find with some accuracy. One thing that we can do is to substitute these values that we computed, these roots here, we can substitute them to the original system. So we can substitute them for x in the original system. For example, if we take minus 1.295 and we substitute this for x in our original system, we will get these two equations. These two equations has just a single solution in y. As you can see, they no longer depend on x, because for x we have substituted the value. So we solve it for y, and the single solution is minus 1.077. So it turns out that minus 1.295 and minus 1.077 is one of the solutions of our system. In fact, if we look back at the picture, this is exactly minus 1.929 is this one. So this is precisely this solution. And we can proceed the same way with other roots of eliminant, the other roots of this univariate polynomial in X, and substituting them one by one to the original system, we will get the corresponding roots of Y, and that way we will solve the system. This is a quite straightforward strategy, a very simple one. However, it's not the best one because it can suffer from accumulation of rounding errors. As you can see, once we eliminated the variable, one of the variables, we arrived at a polynomial of quite a high degree. So the roots of this polynomial are only approximate. So once we substitute this approximate root for x, we arrive at approximate equations, not just approximate roots, but now we have approximate equations for y, and we solve this approximate equation only approximately because they have too high degrees. So we arrive at approximations of the root of approximated polynomials. For two variables, it's not that bad yet. However, if we imagine that we have a system of many equations with many variables, and we solve it back substituting one by one, variable after variable, we will have we will stack these approximations on each other. So all in all, the final solution, the approximation of the final solution can be quite bad. We may have very big rounding errors this way. Of course, there are methods to improve this solution. After all, we can use some kind of multivariate Newton approximation and things like that. However, there is another strategy, an alternative method, is to eliminate another variable. In the first case, we eliminated y, and we arrived at a univariate equation for x. But, nothing prevents us from eliminating x. We can get rid of the x, eliminate it, and get a univariate polynomial in y. And then the roots of this univariate polynomial will be the projections of, will be again the projections of the solution of our original system, but this time on the vertical axis. So these will be the ordinates of the solutions. So in our case, the real roots of this degree 8 polynomial are these 4 points. Visually, these look like this. We eliminated y, and we got the projections on the OX axis. And by eliminating y, we had this polynomial, and the roots of this polynomial were the projections, were the abscissas of the solutions. Eliminating x, we project the solutions onto the y-axis, so we arrive at this polynomial, and the roots of this polynomial are just the ordinates of the solutions of our system. So when we pair them, we consider every possible x and every possible y, and we numerically check all the possible pairs. So for example, we will try this one for x and this one for y. It turns out that we do not have 0, so this is not a root. But if we check this one for x and this one for y, with expected accuracy, we arrive at 0, so this is one of the solution. And so on and so on. We try all the possible pairs, and we identify which of these pairs are the solutions. And this way we have quite a high accuracy, because we approximate the roots independently in x and y. This way, we have some general idea what the elimination theory is all about. This gives us some rough idea what we are going to do today. So now we can turn into some details how to eliminate the variable from a system of polynomial equations. The first thing that we need to learn is the notion of monomial orders. Recall that some relation on a set A is called a linear order if it satisfies the following four axioms. So first of all, every element is in a relation with itself, so the relation is reflexive. Secondly, if we have two elements, A and B, of a set A, such that A is in a relation with B and B is in a relation with A, then A and B must be equal. This is antisymmetry. Third property, third axiom is transitivity. So if A is related to B and B is related to C, then A must be related to C. And the last axiom is totality. So if we take any two elements, then either A is related to B or B is related to A. So you can see that these axioms generalize the standard notion of weak inequality. So we can think of this relation as a weak inequality, less than or equal to. In fact, this is a generalization to this to any set. And the set that we are interested in is the set of monomials in multiple variables. So let us consider a ring of multivariate polynomials with coefficients in some field. For short, to avoid too excessive notation, I will write C alpha x alpha just to denote a term with many indices. So this alpha is a multi-index. So in fact, this is alpha 1, alpha 2, up to alpha n. So this x alpha means the alpha 1 power of x1 times alpha 2 power of x2, and so on, alpha n power of xn. And now we'll consider the set of all these possible monomials, so all the possible products of powers of variables. This set admits just a single operation. This is multiplication. Of course, if we multiply two monomials, we will arrive at a monomial. So the set of monomials is so-called a monoid. A linear relation on the set of monomials is called a monomial order if it satisfies three additional axioms. First of all, the unit element, which is a monomial with where all the exponents are zero, this unit element is smaller than any non-unit element in the set with any other monomial. Secondly, if we select any non-empty subset of monomials, then this subset must have a minimum element. And the third property says that this relation is compatible with multiplication. So if x alpha is related to x beta, then if we multiply both sides by some x gamma, the relation will be preserved. Such a relation is called a monomial order. Before I proceed any further, let me present four standard monomial orders, four monomial orders that are in some sense canonical. First of them is the lexicographical order, abbreviated LEX. And this order works like this. If we have such multivariate monomials, we compare the exponents starting from the leftmost one. So if we examine them from left to right, and if we encounter the first two exponents when differ, so alpha and beta on some position differ, then the monomial with lower exponents is the smaller element with respect to this lexicographical order. The second order is graded lexicographical order, abbreviated to GLEX, or the alternative name is degree lexicographical order, and this is abbreviated to DEGLEX, and both these names refer to the same order. Here we first look at the total exponent, total degree of both monomials. So here, by this absolute value of alpha and absolute value of beta, we understand the sum of all alphas, alpha 1 plus alpha 2 plus alpha 3, and so on, plus alpha n, and the same about beta. So if the sum of exponent of one element of one monomial is strictly less than the sum of exponents of the other monomial, then this monomial with a smaller sum of exponents is considered smaller with respect to graded lexicographical order. If the two sum of exponents, so these total degrees, are equal, then we just use lexicographical order and we compare them with the lexicographical order. First of this list of standard orders is the reverse lexicographical order, abbreviated to REVLEX. This is completely reversed with respect to lex. First of all, we read the exponents from right to left, not from left to right. So we first look at the last exponent instead of looking at the first exponent. And then, if we find a discrepancy, if we find two exponents that differ, then the element that the monomial is considered smaller if its exponent is bigger. So we reverse the direction of the inequality. So x alpha is smaller than x beta with respect to the relation REVLEX if in the last place where the two exponents differ, the exponent of x alpha is greater than the exponent of x beta. And finally, the last one of these standard form orders is the graded reverse lexicographical order, alternatively called degree reverse lexicographical order, abbreviated to GREVLEX or DEGREVLEX. And GREVLEX is related to REVLEX in the same way as GLEX was related to LEX. Namely, first of all, we look at the total degrees. If the total degrees differ, then the monomial with a smaller total degree is considered to be smaller with respect to GREVLEX. So if the sum of alphas is less than sum of betas, then x alpha is less than x beta. If the two total exponents are the same, then we revert to REVLEX and we compare these two monomials with respect to REVLEX, so right to left, and the smaller one is the one with a higher exponent. So let me show how this works on a specific example because it is much easier to understand it this way. We want to order the terms of a polynomial f that you can see here with respect to these four monomial orders. The three monomials that appear here are x, y square, z, x, y, z cube, and x square, z square. So if we look at the exponents, assume that the variables are read left to right, so x is the first one, then y, then z. Then exponents are here 1, 2, 1, 1, 1, 3, and 2, 0, 2. For the lexicographical order, we read the list of exponents from left to right. So first we look at the leftmost exponent. Here we have 2, here we have 1, here we have 1. 2 is the biggest number, so this monomial is the biggest of all these three with respect to lex, so it comes as the first one. Now we compare these two guys. We have 1 and 1, so the first exponent does not differ. Now we have 2 versus 1. 2 is bigger than 1, so this monomial is bigger than this monomial, so this guy comes as a second on the second place, and this guy comes on the third place. So this was lex. And now let us look at glex, graded lexicographical order. So first of all, we must look at the total degree of each of the monomials. So we need to look at the sum of exponents. So here we have 4, here we have 5, and here we have 4. Of course, 5 is bigger than 4. So this guy is the biggest of all these three monomials with respect to glex. So this guy comes first. Now we have 4 and 4, so the total degrees are the same. So we compare these two guys with respect to lex. So we read the exponents left to right, so we have 2 versus 1. So this guy comes in the second place, and this guy is the smallest of all of them with respect to graded lex. Now comes the revlex, reverse lexicographical order. So now we read the list of exponents from right to left, and we select the smallest of all these three exponents. So we have 1, 3, and 2. 1 is the smallest exponent, so this monomial is the biggest one with respect to reverse lexicographical order, so it comes in the first place. Now we have 3 versus 2, so this guy is bigger than this guy, so this guy comes at the second place, and this is the smallest of all these three monomials with respect to reverse lexicographical order. And finally, we have grevlex, graded reverse lexicographical order. So again, first we look at the sum of exponents on the total degree. We have 5, 4, and 4. So this guy is the biggest of all of them, so it comes here. And now we compare these two guys of the same total order. So we use the list of exponents read from right to left. So this 1 versus 2, so 1 is smaller, so the monomial is bigger. So we have 2xy square z and xy z square. Let me comment a bit on that, because first of all, it of course influences the order of monomials of a polynomial, order of terms of this polynomial. But this is not just a question of aesthetics and how we write and how we present it. This is more a question of efficiency of computations. In fact, the orders influence not only the speed, but even whether you can do some computation or you can't do some computation with a given polynomial. The general rule of thumb is that the lexicographical order gives you the most possibilities as far as the possible computations go. So the most operation that can be done with just the lexicographical order. On the other hand, the lexicographical order is usually the slowest one to compute. So if we can do something with lexicographical order and some other order, then usually the lexicographical order will be slower. However, there are operations that can be done with the lexicographical order and can't be done with other orders. On the other hand, the graded reverse lexicographical order is usually the fastest of all 4 of them. So usually the computation with respect to grevlex are much faster than the others. However, the number of operations that are possible with grevlex is the most limited. So there are operations that you cannot do with this order. If you can do it, then this order will be probably the fastest one. However, some operations, especially the ones associated to elimination theorem that you will learn today, are most limited, and in fact they cannot be performed directly with grevlex. So this is a general comparison of these different orders. Once we have introduced the different monomial orders, we can introduce some more notation. So suppose we are given a polynomial in variables x1 to xn, and we have ordered its terms in a decreasing order with respect to some monomial order. So we have the sequence of terms, and the first monomial is the biggest of all of them. By the support of the polynomial f, we understand the set of all these monomials that occur here with non-zero coefficients. The leading monomial is, of course, the monomial which is biggest of all of them. And the leading coefficients is the coefficient that comes with the leading monomial. And finally, the leading term is just the product of the leading coefficient and the leading monomial. So the terminology is the following one: x alpha, so x1, alpha 1, x2, alpha 2, and so on and so on. The product of all of them is called a monomial. If we multiply it by a coefficient, we call it a term. So this is a term and this is a monomial. One may wonder why we haven't talked about monomial orders when we were dealing with univariate polynomials. The reason is that for univariate polynomials, we have just one monomial order. The only monomial order for univariate polynomials is just the order of exponents. There is nothing else we can do here. So the only possible monomial order for univariate polynomials is just the comparison of exponents. That's why we do not consider here the term of monomial orders. The monomial orders are important only when we deal with multivariate polynomials. Next thing that we need to introduce in order to be able to talk about Grobner bases is the notion of multivariate polynomial reduction. This is a common generalization of division with remainder for univariate polynomials, and a Gauss reduction that you know for multivariate systems of linear equations. The common generalization of both these terms is called a multivariate polynomial reduction. So let me define this term now. I will say that polynomial f reduces in one step to polynomial h modulo a polynomial g if, first of all, the leading monomial of g divides one of the monomials of f. So there is a monomial in f which is divisible by the leading monomial of g. And so when we divide it, so we have f minus, now we reduce this term here. So we have this term of f over this leading term of g times g. So this guy will cancel, and we arrive at the polynomial h. So this is called reduction in one step. We now say that a polynomial f reduces to polynomial h modulo a set of polynomials. Here we do not consider a single polynomial, we consider the whole set of polynomials, and we denote it f arrow g to h. So f maps reduces to h modulo g. If f reduces to f1 modulo 1 of this polynomial, this guy reduces to f2 modulo another polynomial, and so on and so on. And finally, we arrive at polynomial h. The polynomials here, modulo which we reduce in a single step, don't need to have be all the polynomials of G. They don't need to have any special order. We can select them in whatever order we wish to. So we can first take say G3, then G1, then G7, and then G1 again, and so on and so on. If after finitely many steps, starting from f, we arrive at h, we say that f reduces to h modulo the set G. And if this polynomial h cannot be reduced any further, then we say that it is a remainder of f modulo the set G. So the algorithm for computing the remainder of a polynomial is quite straightforward, and if you look at it, it closely resembles the algorithm for dividing a polynomial, a univariate polynomial with a remainder. So as an input, we have a polynomial and a set of polynomials modulo which we will reduce it, and we have some fixed monomial order. We start with initializing R to be the polynomial f, and we repeat indefinitely the following steps. So we look for all the terms of R and all the polynomials of G. So we have in fact 3 loops here. Here is while loop, and here are the 2 for loops. So this is while we don't have a remainder, and this loop will be break here. We will break out from this loop here, from this outer loop, and here we have 2 loops, for one for all the terms of R and one for all the polynomials on G. If a leading monomial of the polynomial Gi divides a given term of R, then we just reduce it. So if we find a term of R which is divisible by the leading monomial of one of the polynomials here, we just reduce R, we replace R by this reduction by single step. If there is no such a polynomial, so no such monomial and no such polynomial Gi and no monomial xi, then R is the remainder we are after, so we just return R and we quit. As I said, this is a generalization of Gauss elimination. In fact, let me show how it works on the example where we have just a system of linear equations. So we consider the system of linear equations. So this is our f1, this is our f2, and this is our f3. And we wish to reduce f2 and f3 modulo f1. So we want to reduce f2 modulo f1. So we have something like this. I will do the computation by hand, so you can see all the stuff what happens here, all these things that happen here. So we have 2x plus y minus z plus 1. This is our f2 minus, and now we have this is the leading monomial. This is the leading monomial of f1. And it's obvious that this leading monomial divides this term here. So we have 2x over the leading monomial of the leading term of f1, which is x, times f1, x minus 2y plus 3z minus 2. So this is obviously the x's cancel here, so this x cancel with this x. So what we get is 2x plus y minus z plus 1 minus 2x minus 4y plus 6z minus 4, and this is 2x minus 2x will cancel, so this guy cancels with this guy. This is how it was designed, so that the terms will actually cancel, and we have y minus and minus 4y, so it's 5y. Now we have minus z minus 6z, so it's minus 7z, and we have 1 plus 4, it's plus 5. So this is the f2 modulo f1 is 5y minus 7z plus 5. So f2 reduces to this polynomial modulo f1. In the same way, we can reduce f3. So if we reduce f3, we'll have this guy. So we get rid of x. Now the leading monomial of f2 is the leading monomial is y, and the leading term is 5y. So we can reduce f1 and f3 modulo f2. So if we reduce f1 modulo f2, we will cancel the y here. So we have x plus 1 over 5z. If we reduce f3 modulo f2, we will arrive at this guy, minus 4 over 5z plus 3. And now finally, this will be the leading term of f3, so we can cancel these guys here. So we will reduce f1 modulo f3 to cancel z here, so we have this guy here. And we can do the same for f2, so we reduce f2 modulo f3, and we arrive at this guy here. So all in all, we arrive at the solution of our system. As you can see, this was nothing else but just the standard Gauss elimination that you learned at the course of linear algebra. But at the same time, what we did here, we computed the reduced Grobner basis. So this should give you some intuition about Grobner basis as a generalization of Gauss elimination, but a generalization which works for polynomials of any arbitrary degree, not just for linear polynomials, but it will work for polynomials of arbitrary degree. However, one word of warning is that the reminder for in multivariate case, reminder of a polynomial modulo a set of polynomials does not have to be unique. Here the things change a bit. For univariate polynomials, if we computed a remainder of one polynomial modulo another polynomial, the remainder was unique. For multivariate polynomials, one polynomial can be a remainder, but another polynomial, completely different polynomial, can be remainder as well. Let me show it explicitly on the following example. So we have these three polynomials. We have lexicographical order again, x before y. And we have such a polynomial, f, and two polynomials g1 and g2. And we wish to compute the remainder of f modulo g1 and g2. So first of all, I will compute the remainder in the following order. So first I reduce f modulo g1, and then I reduce it modulo g2. So this is the leading monomial, and this leading monomial, of course, this xy divides this monomial of f. It divides x square y. So what we have is x square y plus 3x square minus y square minus x square y over the term of g1, the leading term is xy, times g1, so it is xy plus 2x. Of course, this guy here cancels, so y cancels with this y, and 2 square cancels with this x. And so what we have is x squared y plus 3x squared minus y squared minus, and we have x here, so it will be x squared y plus 2x squared. Of course, these two guys cancel, so this guy and this guy cancel, and of course x squared is here and here, so what we have is x squared minus y squared. So I just showed this part. This is x squared minus y squared, which actually equals g2. So it is not surprising that if we just reduce x squared minus y squared modulo g2, then we arrive at 0. So 0 is a remainder of f modulo g1 and g2. But if we do the reduction in other order, so let's say that we first reduce f modulo g2, what we can do, because this is a leading monomial, and this leading monomial x squared divides this guy, and it divides this guy as well. But for example, we divide this guy. So we'll arrive at 3x squared plus y cubed minus y squared. So here the 3x squared is still divisible by this leading monomial, so we can reduce it one more time, and if we reduce it again, we'll arrive at this polynomial. And this polynomial is a reminder because it cannot be reduced any further. We have two terms here, and none of these terms is divisible by the leading monomial of any of these two guys. It is not divisible neither by xy nor by x squared. We have y cubed and y squared. They are not divisible by x squared nor by xy. So this is again a reminder. This is a reminder, and this is a reminder. These are two different reminders of the same polynomial. So this thing, this phenomenon that a single polynomial can have more than one reminder modulo a set of polynomials is the good place to introduce the notion of the Grobner basis, which is the subject of our today's lesson. First thing is that we need to change perspective of our viewing the system of polynomial equations. We need to introduce an intermediate agent between the system of polynomial equations and the set of solutions. Of course, we start here. We start at a system of polynomial equations. We want to arrive here. We want to arrive at a set of solutions, but it turns out that the direct route is not the simplest one. We need, as I said, to introduce an intermediate agent. So instead of going from here to here, we'll go from here to here and from here to here. So if we look at it, we have a system of polynomial equations, and we want to get a set of solutions. So set of these points in, for example, the vectors in complex numbers, such that all these polynomials vanish at this point. So this point is the solution of this system. But in order to do that, we introduce the notion of ideas in the ring of polynomials. I suppose that most of you are familiar with the terminology of ideas. It must have appeared on the course of algebra. But let me shortly recall that an idea in the ring is such a subset of this ring which is closed under addition and is closed under multiplication by any arbitrary element of a ring. So in terms of system of polynomial equations, if we think about a system of polynomial equations, if we have a solution, let's say P is a solution, then F1 on P, F2 of P, and so on, all of them vanish at P. So if we have two polynomial equations, we can add them the left and right sides, we can add these polynomial equations. So if f1 of p is 0 and f2 of p is 0, then f1 plus f2 at p is 0 as well. So the polynomials that vanish at p are closed, the set of polynomials that vanish at p are closed under addition. On the other hand, if we take a polynomial that vanishes at p and we take any other polynomial, then if we multiply them, so let's say f of p is 0 and g of p is whatever, then f times g is 0 times anything, and 0 times anything is 0. So f times g also vanishes of p. If f vanishes at p, then f times anything vanishes at p. This is precisely the notion of the ideal. The notion of the ideal is the right perspective for considering the systems of polynomial equations. Why it's so? Because we want to replace this system of polynomial equation with another system of polynomial equations which have precisely the same set of solutions, and on the other hand, it's much easier to handle. In terms of ideas, this means that we want to replace one set of generators of the ideal with another set of generators of the ideal, but which will be better behaved. This is precisely the notion of a Grobner basis. In order to provide a precise definition of a Grobner basis, let us consider the following theorem. So we have an ideal and some system of generators of this ideal, and we have some fixed monomial order. Then the following four conditions are equivalent. One of these conditions, the condition number 3, is the one which we started from. The remainders modulo g are unique. In general, we saw that remainders modulo a set does not have to be unique. If this remainder modulo a given set are unique, such a set will be called Grobner basis. The other equivalent condition says that, okay, an element belongs to this ideal, so it vanishes at the same places where this initial polynomial vanishes, if and only if it reduces to 0 modulo this set. Another condition says that if we have a non-zero polynomial in this ideal, then its leading term must be divisible by a leading term of one of the ideals, of one of the polynomials in G. And another condition said that the ideal generated by the leading terms of elements of G is the same as the ideal generated by the leading terms of all the polynomials in I. So this is a set of, so this G is a set of generators with a very special properties. One of them is that remainders modulo this set are unique. And if the set of generators satisfy any, so all these conditions, then this set is called a Grobner basis of this ideal. In short, we just say Grobner basis. One important fact is that every ideal has a Grobner basis. So if we take any ideal, if we take any set of generators, then we can always replace this set of generators by a Grobner basis. So this is a very important fact which let us do all the computations. The way to construct the Grobner basis is via so-called Buchberger criterion. If we look back at this theorem, we can observe that all these conditions, although they are very elegant from the abstract point of view, from the algebraic point of view, they are not very practical, because in every of these four conditions we have to check infinitely many polynomials. For example, if we look at the condition 3, this condition says that G is a Grobner basis if the remainders modulo G are unique. So what we have to do to check this condition directly would be to check all the reminders of all the polynomials in our ring of multivariate polynomials, but there are infinitely many of them. So it is not possible to check this condition directly in a finite time. Likewise here, this condition says that G is a Grobner basis if every polynomial of the idea reduces to 0 modulo G. But okay, there are infinitely many polynomials in the idea. So how can we check it? We would have to check infinitely many polynomials to be sure that this condition holds. The same is this condition. This calls for every polynomial in I. And the same is with this condition. Again, we have infinitely many polynomials. So none of these conditions can be directly checked. But there is a condition which is equivalent to all of them and which is of finite type, for which we need to check only finitely many polynomials. In order to introduce this condition, I need to introduce the notion of the S polynomial. So given two polynomials f and g, and having some fixed monomial order, so we can talk about the leading monomers and leading terms, we consider the following polynomial, the polynomial of the following form. So in the numerators of both these fractions, we have the same expression, which is a least common multiple of the leading monomial of f and a leading monomial of g. Of course, this least common multiple is divisible by both of them. So here we divide by the leading term of f, and here we divide by the leading term of g, and we multiply it once by f, once by g. This expression it can be considered to be somehow related to Bezout identity. I remember that Bruno Buchberger, who invented the whole theory, he admitted that his motivation to developing this theory came from two sources. One source was the Gauss elimination, that we have already observed. The other source was the Euclidean algorithm. And the criterion that I was referring to, the Buchberger criterion, which was probably the starting point of his PhD thesis, says that set G is a Grobner basis if and only if every S polynomial of the two polynomials from this set reduces to 0 modulo G. Observe that here we have only finitely many polynomials to check, because we check only the gi and gj belonging to G, and G is a finite set. So we have only finitely many pairs. In fact, there is no point in checking gi and gi, because the S polynomial of gi and gi is 0, and 0 reduces to 0. And this is antisymmetric, so if we check gi, gj, then the gj, gi is minus this, so if one of them reduces to 0, the other one reduces to 0 as well. So in fact, if G consists of n elements, then we have to check only n square minus n over 2 pairs of polynomials. The first algorithm, again due to Bruno Buchberger, checks whether a set is a Grobner basis. So as an input, we have a finite set of polynomials and some monomial order. And as a result, we return either true when G is a Grobner basis, or we return false if it is not a Grobner basis. But in addition, if it is not a Grobner basis, then one of these S polynomials does not reduce to 0. So in addition, together with false, we return this reminder which is non-zero. This non-zero reminder, it will be useful in the next algorithm. And the algorithm is quite straightforward. This algorithm is a direct implementation of this theorem. So we check every two distinct polynomials of G. We take f, we take g, we construct their S polynomial. We compute the remainder of this S polynomial modulo G. If this remainder is non-zero, then okay, the theorem says that if at least one of the remainder is non-zero, then G cannot be a Grobner basis, so we return false and this non-zero remainder. If the loop finished and we never broke off, we never return false, then it means that okay, all the polynomials, all the S polynomials of every two polynomials of G reduces to zero, so all the remainders are zero, then G is a Grobner basis and we return true. The second algorithm, also due to Buchberger, constructs a Grobner basis from any set of generators. So we are given a set of generators and we return a Grobner basis of the same idea. In terms of systems of polynomial equations, this takes one system of polynomial equations and returns another system of polynomial equations with the same set of solutions, but the second system of polynomial equations each is much easier to handle. The algorithm works like this. We start with G equal F, and we check if it is a Grobner basis using the previous algorithm. If it is a Grobner basis, if the previous algorithm returns true, so all the S polynomials reduces to zero, when G is a Grobner basis, so we output G and we quit. Now there is nothing else to do. Otherwise, this algorithm returned some non-zero remainder. It was not a Grobner basis because there was some non-zero remainder. Then we append this remainder to G and we repeat the steps again and we check, we append this reminder and we check again if it is a Grobner basis or not. Let me show an explicit example how it works. So I want to consider these three polynomials: y square yx, x square, y plus x, y. Here I just consider a lexicographical order when y is greater than x. So I just change the order of variables. So now y is greater, x is smaller. So how does it work? Using the Buchberger theorem, what we need to do is we need to compute the S polynomial of every two polynomials here. So we need to check this guy with this guy, this guy with this guy, and this guy with this guy. So we need to check 5 S polynomials. So let's start with the first one. So we compute the S polynomial of y square plus yx plus x square and y plus x. So according to the definition of the S polynomial, this is a leading least common multiple of this is a leading monomial and this is a leading monomial. So this is a least common multiple of y square y over the leading term of the first polynomial, so over y square times the first polynomial, y square plus yx plus x square, minus again the least common multiple of y square y, the numerators are the same, over the leading term of the second polynomial y times the second polynomial y plus x. Of course, the least common multiple of y square and y is y square, so we have y square here over y square. It's y square plus yx plus x square minus, here is y square over y plus x. So this is the first one. The first fraction is 1, the second fraction is y. So we have y square plus yx plus x square minus y square plus yx. And so this is designed in such a way that the leading terms must cancel, so this cancel. In this case, in addition, we have cancellation of these terms, but this is not standard, but the leading terms must cancel. That's how the as polynomials are designed. So what we got is x squared, and observe that the leading monomials here are y squared, y. So none of them divides x squared, so x squared cannot be reduced any further. So x squared is a remainder, and of course it's non-zero. This remainder is non-zero, so this means that G is not a Grobner basis. But the algorithm says that, okay, if it's not a Grobner basis, then we must append this remainder, this non-zero remainder to G, and check again. So it is exactly what we do. So here was the first step. We computed the S polynomial of these two guys. We got x squared. So G was not a Grobner basis. So we append x squared here. And now we have 4 polynomials to check. And we need to check every pair of them. We need to compute the S polynomial of every two. So these two guys are okay because we have appended x squared. Now we can compute this guy and this guy, y plus x and y, and this actually can be computed just in memory. Of course, these y's will cancel, and we have x left. So the remainder is x, and x cannot be reduced any further because x is not divisible neither by x squared, nor by y, nor by y squared. So x is non-zero remainder, so G is not a Grobner basis. We append x to this G. So we have this guy here. So we have these 5 polynomials. And if we compute the S polynomials of every pair here, we will see that this S polynomials reduces to 0. So this is a Grobner basis. Before we proceed any further, let me explain this example once again, but now from the point of view of polynomial systems. What happens here for the system of polynomial equations? So we started with a system of polynomial equation of the form y squared yx plus x squared equals 0, y plus x is 0, and y is 0. This is our original system of polynomial equations. Of course, I designed this example in such a way that we can directly see what is a solution. If y is 0, then x must be 0 as well, so the only solution is 0, 0. But let me show you what happens to this system when we constructed a Grobner basis out of it. So what we got? We just appended x squared and we appended x. So we arrived at a system y squared plus yx plus x squared is 0, y plus x is 0, y is 0, and the two additional equations what we produced is x squared is 0 and x is 0. So this is a new system which is a Grobner basis. Observe that in this new system we have these two polynomials, these two equations, and these two equations produces just the result. So this is the first Grobner basis that we constructed, and we already see that once we constructed it, we directly got the solutions. However, this Grobner basis is not really what we want. It's a Grobner basis, but not the Grobner basis that we are finally interested in. The Grobner basis that we want to get finally is the reduced Grobner basis. But before I introduce the reduced Grobner basis, first I need to define the minimal Grobner basis. The means for to that is the following theorem. It says that if we have any Grobner basis and we find two elements of this Grobner basis, two distinct polynomials f and g, such that the leading monomial of g divides the leading monomial of f, then we can remove this polynomial f from the Grobner basis, and what we get here, g minus f, is still a Grobner basis of the same idea. So in terms of polynomial systems, this theorem says that if we have a system of polynomial equations which is a Grobner basis, such that polynomials form a Grobner basis, and a leading monomial of one of the polynomials divides a leading monomial of another polynomial, then the later polynomial can be removed from the system, and the set of solutions will not change. Grobner basis is called minimal if no polynomial can be removed from it. So the leading monomial of any polynomial will never divide a leading monomial of another polynomial in this Grobner basis. In other words, it can be proved that the minimal Grobner basis is minimal in the usual sense, so it has a minimal number of elements. The method for constructing a minimal Grobner basis out of any Grobner basis is just a straightforward application of this theorem. Namely, the algorithm works as follows. We start with any Grobner basis, and we compute the minimal Grobner basis, just looping over all the pairs of polynomials g and f, two distinct polynomials g and f belonging to the Grobner basis. If the leading monomial of one of them divides the leading monomial of the other one, then we remove this f from G. And once we did it for all the polynomials in the Grobner basis, for all pairs of polynomials, then what we get as a result is a minimal Grobner basis. Let me continue the previous example. So previously, starting from this original system of polynomial equations, we arrived at a system of polynomial equations such that the left-hand side form a Grobner basis. Now we can minimalize this Grobner basis. I will mark the leading monomials. So this is a leading monomial, this is a leading monomial, this guy, and this guy. So observe that the leading monomial of y plus x, which is y, obviously divides y squared, which is the leading monomial of the first polynomial, the leading monomial of y squared plus yx plus x squared. So this means that we can remove the later polynomial from the Grobner basis, so we can cross out this equation. Likewise, we can observe that the leading monomial of y plus x, which is again y, divides y, which is the leading monomial of y. So we can remove the third equation as well. So we can remove this guy here. Let me stop here for a second because, well, we see that it would be more sensible to remove this equation rather than this one, because this one already gives us the solution, y equals 0, while this one doesn't. But I do it intentionally to remove this one to show you that this procedure, all in all, will finally result in the same system of polynomial equation, which will produce the solution. So although we just looking at this and the system, it would be more sensible to remove this equation rather than this one. But anyway, you will see that all in all, in the final result, we will get the same resulting system of solutions. So it doesn't really matter if we do it this way or this way. It will be the same outcome. So even if the computer does it without just schematically, just takes the first equation and checks all the others and remove those like here, the outcome of this algorithm will be the same anyway. And finally, our final observation is that the leading monomial of the last polynomial, which is just x, because the polynomial is x, divides x squared, which is a leading monomial of x squared. So again, this equation here can be removed. So all in all, what we get here is that the minimal Grobner basis consists of y plus x, 0, at and x is 0. This is a minimal. The left-hand side of these equations are form the minimal Grobner basis. Minimal Grobner basis. So this was the notion of the minimal Grobner basis. So the idea is that we remove unneeded equations from the system. We started with some arbitrary system. We enlarged it to a Grobner basis, and now we minimalize this Grobner basis by removing the equations which do not contribute to the set of solutions that. So the resulting polynomial system, as we can see, this polynomial system, the solutions to this system are 0, 0, so the same as 2 and 2 This does not produce any new solution, and we do not lose any solutions going from here to here. And now the next step is the reduced Grobner basis. Here, the means for that are provided by this theorem, which says that if we have any Grobner basis and we find two elements of this Grobner basis, two distinct elements, then we can reduce f modulo g to some new polynomial h, and if we replace f by h, so we remove f but we append f h, then what we get as a result is again a Grobner basis of the ideal I. So any element of a Grobner basis can be replaced by its remainder modulo other elements. So this leads to the notion of a reduced Grobner basis. A Grobner basis is called reduced if we cannot reduce any of the elements of this Grobner basis any further. So recalling the notion of a remainder and recalling the notion of the reduction of polynomials, this means that the leading monomial of any g cannot divide any monomial of any other polynomial. Here we don't take leading monomials because we get rid of these polynomials where leading monomial of one divided by leading monomial of the other at the stage of minimization. Here we take any monomial from the support. So the Grobner basis is reduced if the leading monomial of any polynomial will never divide a monomial of any other polynomial. In addition, the second axiom is that all the polynomials are monic. So the leading coefficient of every polynomial is 1. This is mostly to ensure that the reduced Grobner basis is unique. But the really important axiom is this one. And the algorithm that produces a reduced Grobner basis out of a minimal Grobner basis is again a straightforward application of the preceding theorem. So first of all, we normalize all the elements. So we divide every polynomial g in this Grobner basis by the corresponding leading coefficient. And then we loop over all the polynomials in this Grobner basis, which is already minimal, which we assume that is minimal. We loop over them, and we compute the remainder of g modulo all the other polynomials. Of course, we cannot include g itself here because then the remainder would be 0. We compute the remainder of g modulo the other polynomials. And then once we computed the remainder, we replace g by r. So we substitute, we remove g from the basis and we append r to the basis. after doing it for all the elements, we arrive at the reduced Grobner basis. Once again, let me show it on the example. I will continue the previous example. So now I will have the leading monomial is here and the leading monomial is here. So if I reduce y plus x modulo x, so this is nothing else but y, according to the formula that was here on one of the previous slides, is 1 plus x minus, and here is x over x time x. So this is clear, but it is y. So y plus x is replaced by x. So this minimal Grobner basis is reduced to the following Grobner basis. So in place of y plus x, we replace y plus x by the remainder by y. So it's y equals 0 and x equals 0. And this is a reduced Grobner basis. This is reduced. And you can see here that once we have this reduced Grobner basis, this actually gives us the exact solution of our system of polynomial equations. So we started with these polynomial equations. We enlarge it into a Grobner basis. We minimalize the Grobner basis to a minimal Grobner basis, and we reduce it to a reduced Grobner basis. And this reduced Grobner basis gives us the final answer, gives us the solution of the system. This is not an accident. You will see in a moment that the elimination theorem that explains this phenomenon. But before I present the elimination theorem, let me mention the theorem of Buchberger, another theorem of Buchberger, which says that every ideal has a unique reduced Grobner basis once we fix the monomial order. This is a very powerful theorem which allows us to operate directly on ideals. This is one of the few facts about Grobner bases that make them useful not only for elimination theory, not only for solving polynomial equations, but for a general computer algebra. This theorem let us represent ideals by their unique Grobner basis, and this theorem allows us to do computations with ideals, so which is very useful outside the realm of just polynomial equations. So all in all, the whole idea of working with polynomial equations is the following one. We start with a set of generators of an ideal, so as the initial system of polynomial equations. As you have seen it, we enlarge it. We use the Buchberger algorithm to append the reminders of the S polynomials until we arrive at the Grobner basis. This will possibly be quite a large system of polynomial equations, but it will already be a Grobner basis. Then we cross out, we removed the polynomials which are not needed, which do not contribute into the solution, which are dependent on the other polynomials. And then finally we reduce this minimal Grobner basis to get a nice one, which is a reduced Grobner basis. So the last step towards solving the system of polynomial equations is the elimination of variables, so-called elimination theorem. In the elimination theorem, we assume that the set of variables is divided into two parts, which I denoted here x's and y. So there are some variables denoted x, and some variables denoted y. And the assumption is that the monomial order is such that monomials with respect to x's only are bigger than monomials that involve y's only. For example, the lexicographical order is such an order because the variables in the monomials that involve only xn will be always smaller than the monomials involving only xn minus 1, which are always smaller than monomials involving only xn minus 2, and so on and so on. So the lexicographical order satisfies this assumption no matter when we split the list of variables. And then we have a Grobner basis with respect to this monomial order of some idea, and the elimination theorem says that if we intersect with Grobner basis with the ring of polynomials in y's alone, so without any x's, then this set will be the Grobner basis of the ideal intersected with this ring. This theorem may look intimidating at the first sight because it can look complicated and quite abstract. However, it is quite straightforward if we observe how it works on a specific example. The example will explain what this theorem does. This theorem says that if we compute the Grobner basis with respect to a monomial order that satisfies this condition, then this Grobner basis will contain polynomials that depend only on y's. So if we order variables from the biggest one to the smallest one, then the corresponding system obtained by the Grobner basis will be triangular. So there will be a polynomials depending on the fewest number of variables, then there will be polynomials depending on more variables, and so on and so on. As I said, it's best observed on a specific example. So suppose that we are given the following system of polynomial equations in three variables x, y, and z. Doing it by hand, computing it without any special tools, could be quite complicated because it contains polynomials of degree 2 and 3, so it's not straightforward. However, we can now apply all this machinery that we constructed throughout this lecture. So first of all, we change the system and we introduce the notion of ideal. We write it as an ideal generated by these four polynomials. Then, as a next step, we enlarge the set of generators so that we construct a Grobner basis. So from the previous set of generators, we construct a Grobner basis with respect to the lexicographical order, when z is the biggest variable and x is the least variable. Observe that already here we see that the system is triangular. We have two polynomials that depend on x only, then we have a polynomial which depends on x and y, and then we have a polynomials that depend on x, y, and z. This one depends on x and y as well, but this one and this one depends on x, y, and z, or on all three variables. However, this is just a general Grobner basis, and the next step we observe that we need to minimalize this Grobner basis. So we remove the polynomials which are not needed. How we can do that? As observed earlier, we have here is the leading monomial, here is the leading monomial, here, okay, these are the leading monomials. And so observe that, okay, we have here for example here, x6 divides x7. So the leading monomial of this polynomial divides the leading monomial of this polynomial. So we can get rid of this polynomial. It's not needed. Likewise, this y here divides y squared. So this leading monomial divides this leading monomial. So this polynomial is not needed. So we can get rid of it. We can remove it. And here we have the leading monomial z, and here we have leading monomial z squared. So this leading monomial divides this leading monomial. So again, this polynomial can be removed from the system. So all in all, we arrive at the following minimal Grobner basis. However, this minimal Grobner basis still can be reduced somehow, because if we observe that we have a leading monomial y here and y appears here, so for sure we can reduce this polynomial and get rid of y here. So our next step is to compute the reduced Grobner basis. So we remove this sum of the terms and we normalize all of these polynomials. So this is reduced Grobner basis with respect to the Lex order. And now we apply the elimination theorem, which says that since we have we're working with Lex order, so if we intersect this ideal with R of x, with just a ring of univariate polynomials, we will get the solutions with respect to x. So this is the polynomial that depends on x alone. If we intersect this Grobner basis with a bivariate, with a ring of bivariate polynomials Rxy, then we get these two polynomials that depend on x and y alone. They do not depend on z. We eliminated z from here. And then finally we have a whole Grobner basis which depends on x, y, and z, and all of them. So we can now solve this system starting from the univariate polynomial equation. So we can first compute the roots of this polynomial, where we learn how to do it on the previous few lectures. This was a polynomial of degree 6. So here we have 6 roots of this polynomial. 2 roots are real, this one and this one, and there are 2 pairs of conjugate complex roots. And now we can apply any of the 2 strategies explained on the beginning of the lecture. So we can either back substitute these values for x, or we can keep eliminating other variables. For example, I substitute these values for x, these roots for x. So if I substitute 0 for x, I have 0, 0, 0. So one solution of the system is 0, 0, 0. If I substitute 1.46, then the solutions are here. So the point 1, 0.46, 0.829, and minus 0.316 is another solution. And here are the 4 remaining solutions. So this way, using Grobner basis and using the elimination theorem, we were able to solve a system of multivariate polynomial equations. So this is a solution of the system. In the remaining part of the lecture, let me present you some other applications of Grobner basis and elimination theorem, so that you can see how versatile a tool it is. So the another application is curve implicitization. Let me first explain what curve implicitization is. There are 2 ways of representing curves or surfaces. One way is to represent them in a parametric form. This is an example of a parametric form. So in a parametric form, a plane curve, on a plane would be represented as x as a rational function of some variable of some parameter t, and y is some as a rational function of parameter t. So you can see it here. So x is t squared minus t over t squared plus 1, and y is 2t over t squared plus 1. This is one way of representing a curve, a parametric one. The another way of representing curve is to write explicitly its algebraic equation in x and y. So this representation would be some polynomial in x and y is 0. So when the curve is the set of zeros of this polynomial. The same can be done for three-dimensional curves. Then we'll have x of t, y of t, z of t, or for the algebraic representation we'll have two polynomials, f of xyz equals 0 and g of xyz equals 0. And the same can be said about parametric surfaces. When x is a rational function in two variables, let's say u and v, y the same and z the same, or we have a polynomial in three variables, f of x, y, z equals 0, and then they have an algebraic representation. Both representations are very useful, but for different purposes. So this representation, this parametric representation, is useful for modeling shapes. It is used in geometric modeling. So, for example, when one creates a project of a car or a ship or whatever, one creates a shape using just the parametric representation. So it is useful in a computer-aided design and things like that for constructing, for designing shapes. On the other hand, the algebraic representation is very useful for analyzing shapes. So, for example, you can imagine that someone designs, prototypes a shape of well, a ship, for example, or a car or whatever, and then we need to analyze this shape just to check, for example, whether the shape doesn't, where the curve does not contain any points of self-intersection, because of course one cannot manufacture a car with self-intersecting hull. It is impossible in a physical world. Shape where in the cross section of a car, cross section of a ship cannot self-intersect, and in detection of such things like self-intersection, singular points, things like that, is very similar in the algebraic representation when the curve is represented as solution of a polynomial or a polynomial system. So it is very important to for applications to find a method to go from one representation to the other. So once we have a parametric representation, we want to find the algebraic representation. So the designer constructs, invents some shape, designs some shape, and then this shape needs to be, and this shape is of course in parametric representation because it is how the CAD, computer aided design software, works, and this shape needs to be converted then to algebraic representation to analyze this shape, to check whether it is correct, whether it does not contain any singular points and things like that. And here in this example, I will show you how to use, how to apply Grobner basis to curve implicitization, to changing the representation from parametric to algebraic, to implicit representation. So assume that we are given a parametric curve of this form. Or more generally, I can say that, well, we have x is f of t over h of t, and y is g of t over h of t. So we have a parametric curve given this way. We need to change this into a system of polynomial equations. These are not polynomials, but we can just clear the denominators and we arrive at this system as x times h of t minus f of t is null and y times h of t minus g of t is null. And this is already a system of polynomial equations. And what we want to get, move from here, from these two polynomials in three variables, x, y, and t, we want to get a single polynomial without t. We need to eliminate t. We want a polynomial in x and y alone. So we have this idea generated by these two polynomials. So here are t squared plus 1 times x minus t squared minus 1 and t squared plus y times y minus 2t. We compute the Grobner basis with respect to the Lex order where t is the biggest variable because we always eliminate the biggest variable. And if we compute this Grobner basis, we see that this Grobner basis consists of these three polynomials. So because this is elimination order, the elimination theorem ensures that this is triangular. So there is a polynomial here in this Grobner basis that does not depend on t. So this polynomial describes our curve. So this curve, this original curve, this ellipsis, is given by this equation. So this is the equation of this curve. So this is a parametric representation of this curve, and this is the algebraic implicit representation of the same curve. So this is an example of the application of Grobner basis to computer-aided design, to converting representation of a curve. This same can be used with surfaces. I just did it for curves here because I wanted the whole example to fit on just a single slide. And next example is even more striking because this is a very untypical, unexpected, unintuitive application of a Grobner basis. We will color a graph. Again, for educational reasons, to fit everything on a single slide, I use here a very simple graph, but the method is general. It works with whatever graph you have, providing that you have enough of computer power. So the idea of graph coloring is that we have a graph with some vertices connected by edges, and we want to assign some colors to the vertices in such a way that vertices connected by an edge, so adjacent vertices must have two distinct colors. So for example, vertex 1 must have different color than vertices 0, 2, and 3. Likewise, vertex 2 must have distinct color than 0, 1, and 3. So how we can do it using Grobner basis? First of all, to every vertex we assign a variable. So if we have 4 vertices here, then we have 4 variables here, x0, x1, x2, x3. Every vertex is represented by a single variable. Now we represent colors by roots of unity. For example, we want to color this graph using 3 colors, which is possible for this graph. So we have 3 roots of unity. So let psi be the primitive root of unity of degree 3. The notion of a primitive root was on one of the first lectures when we talked about Fourier transform. So let's say, and we just take all 3 roots of degree 3 of 1. So psi is the primitive root of unity, psi square is another primitive root of unity, and 1 is of course a root of unity. And we assign the colors to these three. Let's say 1 is red, psi is green, and psi square to be blue. Since every vertex must be assigned one of these colors, so for every vertex we have an equation of this form that such that the third power of xi is 1. So for every vertex we have this equation. So this four equation says that every vertex is assigned one of these three colors. In other words, that every xi is assigned one of these three values, one xi square. But the graph coloring requires that the adjacent vertices has two distinct colors, so it is natural to add some inequalities to our system. So if I and j is one of the edges, belongs to the list of the edges, then xi must be different from xj. Unfortunately, the Grobner basis works with polynomial equations, not polynomial inequalities. So we must change this inequality to an equation. But fortunately, it's quite easy because we know that xi cube is 1 and so is xj cube. So it follows that the difference xi cube minus xj cube must be 0, but now this difference can be written as xi minus xj times xi square plus xi xj plus xj square. We know that this must be non-zero, so it follows that this must be 0. So for every edge in our graph, for every edge connecting the vertices I and j, we arrive at an equation xi square plus xi plus xj square equals 0. So here we have 5 edges, so we have 5 corresponding equations. So for example, 0 and 2 are connected by the edge, so we have an equation x0 square plus x0 x2 plus x2 square equals 0. So what we do now? Now we have a system of polynomial equations and we use Grobner basis and elimination theorem. So we apply the Grobner basis we compute the Grobner basis with respect to the Lex order, and the elimination theorem says that the result is a triangular system. Indeed it is. Here we have one equation which depends on x3 alone. Here we have equation which depends on x2, x3. Here we have an equation which depends on x1, x2, x3. And this one potentially can depend on all of them. In fact, in this specific graph, it depends on just x0 and x3, but okay, it may depend on all of them. So this is a triangular system. So we solve it starting from the bottom equation. This equation has 3 solutions, so we can choose any of them. So in other words, this says that we can assign any of these 3 colors to this vertex. So assume that we assign red to this one. So we have x3 equal 1. So if we substitute 1 for x3 here, we have these 3 equations. So this equation has just 2 solutions, xi and xi square. So we just select any one. So in other words, we can assign to this vertex either green or blue, but we cannot assign red. This equation says exactly this. So let's say that we select x2 to be xi. In other words, we assign green to this vertex. So this is green. So now we have just unique solution for x1 and x0. So x1 is xi square and x0 is 1. So the two remaining solution is x1 is xi square and x0 is 1. And this way we colored the whole graph. In the last example, I will return to the problem which I presented on the very beginning of this course, on the very beginning of the first lecture, namely the problem on the inverse kinematic. Now we have all the means needed to solve this problem in full generality. So what's the problem is? Suppose that we have some kinematic chain in or two or three dimensions. So this is a set of points, vertices or joints of this robot. So this is, for example, this point, and this point. The joints, or probably this point, and this point, and this point. So the joints of the robot, the places where this robot can, the segments of this robot can rotate. These joints are connected by rigid segments of length L1 up to Ln, and they can rotate in three or one or three axes, and the rotation is described by the angles phi I x, phi I y, phi I z. We have, in addition, we have an effector, the point where we want this last segment to be placed, and we have the desired angle such that this effector must be approached from this angle. So, for example, imagine that this robot is expected to weld a car. So this effector is moving through the trajectory where this welding is expected to happen. So this problem is to solve this system of equations. So the last point, an, must be placed at the expected position, and the angles must coincide with the expected angle. For simplicity, just to explain it easier, because the method works for 2 and 3 dimensional in the same way, but to fit everything on screen, I will draw it in 2 dimensions. This will result, or this will already result in quite a long equation at the very end, as you will see. If I did it for 3 dimension, the equation would not fit on a single slide. So we have, let's say, 4 points and the effector. We want A3 to be placed here. We want to find the angles here, here, and here, in such a way that A3 is moved here and approaches this point A from a specific angle. So what we are given? We are given the effector. We are given the angle psi. Without loss of generality, we can assume that A0 is the origin. We can always fix the coordinate system in such a way that A0 is placed at origin. And now we use basic trigonometry. For simplicity, I will also assume that all the segments are of length 1. So a simple trigonometry says that if we have 1 here, then here we have cosine, and here we have sine. So the coordinates of A1 are cosine and sine of phi 1. The same applies to A2, but we need to compute the coordinates starting from here. So the two angles add, we have this angle, we add this angle, and we add this additional vector here. And since we want this last segment to approach A from the direction psi, we can compute phi 3 just subtracting these two guys. So applying this equality to the formula of sine and cosine of the sum, we get the formula for A3. So our problem is to find the angles phi 1 and phi 2 such that A3 equals E equals the effector. The last point is in the effector. This equation already ensures that the angle of this last segment will be the one we expect it to be. So using the formula for A3, this can be written a trigonometric vector equation. We can rewrite it by substituting Ci for cosine phi I, Si for sine phi I, and Cs for cosine and sine of psi. So this way we arrive at the following vector equation, which can be rewritten as a system of polynomial equations in these four variables C1, S1, C2, S2. However, the problem is that if we write it this way, we forget that these are expected to be sines and cosines of the angles we are looking for. So this is not good, because if the solution is, for example, that C1 is 10, then such a solution is useless, because we know that C1 must be cosine of phi 1. It cannot be 10. So what we need to do, we need to append additional equations that ensure that that this will be sine and cosine. Namely, we append the trigonometric identity. The trigonometric identity will ensure that these are sines and cosines. So we arrive at the following system of polynomial equations. And now we are on familiar grounds. We can apply all this Grobner basis theory that we developed. So we write it as an ideal. We compute the Grobner basis with respect to the Lex order. We minimalize and reduce this Grobner basis, so we arrive at this and this system of generators, and we write it as a solution, as a system of polynomial equations, and observe that this system of polynomial equation, although it is very big, it may look intimidating, but in fact it is very simple, because the only variables that we need to solve are marked in red. These are S2 square, so square of sine of phi 2, this is cosine. S1, C1 are sine and cosine of phi 1. So all the remaining variables that appear here are just the parameters, are just xe and ye, which are the position of the effector, s and c, which are the sine and cosine of the expected angle psi. So these are the parameters which are feed to our kinematic system. So these are the position and the angle of the effector that we want. So as you can see, this system is basically solved. So S2 is the square root of this guy, or minus this guy. So the angle phi 2 will be just the arcus sine of the square root of this guy. Phi 2 will be the arcus cosine of this guy, and once we have S2 here, and we can substitute it here and here, we can compute the phi 1 by taking the arcus arcus sine, arcus cosine of these guys. So observe that all these things, once we solved it, we used all this heavy machinery of Grobner basis to solve the system. The system is solved analytically. We have an explicit formula for this solution. So this explicit formula can be programmed, can be coded into form of a program which will drive this robot. So for driving this robot, we do not need any strong computer algebra system, because we solve this system. We have an explicit closed form formula for the solution here. This is this formula. We just plug these parameters, and we got the solution, we got the angles. So this can be implemented into some microcontroller of a robot, and it works. So this is an explicit example how we can use Grobner bases in applications.
That's all for today. Thank you very much for your attention. That way we have completed the course of computational mathematics. As I said at the beginning, it was a mini course consisting of only 15 hours. However, I hope it gave you some overview what computational mathematics and especially symbolic computations are about. Starting from absolute beginnings, starting from absolutely basic results like arithmetic of polynomials, we developed all the tools up to very modern, very contemporary results like Grobner bases that we talked today. That's all, folks. Thank you very much.